Okay, so I thought today we'd look at another example involving linear drag. We'll eventually get to a two-dimensional version of this. But I want to look at an object of mass m that's being thrown downwards. So we're starting up above the ground and we're throwing it straight down with a speed v naught. And let's assume that that v naught is greater than the terminal velocity. I'll remind you what that is in just a sec. And what we want to know is, what does the speed look like, or what does the velocity look like as a function of time? Can we get the position as a function of time? What would this look like graphically if we tried to look at it? So this is just sort of a review of how to solve that particular differential equation. We'll start by writing down the net force in the y direction. And as always, I am going to choose my positive y direction to be upwards, just because I'm used to that. And in that case, we're going to have to write down the forces that are active. So we definitely have an mg downwards. And then we've got this drag force, which I'm still going to write in terms of mass times something I'll call gamma. That's going to be my drag coefficient. The direction you might worry about, thinking, well, if it's moving down, then the drag force will be up. Yes, that's true, but I'm still going to write it like this. And the reason I'm writing it like this is because Vy itself is a component of the velocity, which means it can have a sign. It can be positive, it can be negative. And in this case, it's negative. So a negative negative would indeed be in the positive direction. This is the general version because drag should always just be opposite the direction of velocity. So don't put in an extra negative sign here. And then quite generically, we know that this will equal mass times acceleration. That's just what Newton's second law says. And I'll go ahead and rewrite that as dvy dt. That's the time derivative of the y velocity. So now, like before, all of the masses cancel out. That's kind of why I chose that drag coefficient to have that form. And then we're going to do separation of variables and solve for my velocity as a function of time. So let's do that really quickly. We've seen it before, but just as practice. Okay, so first I separated my variables. Notice that I can factor out the negative sign here. I'll leave it with the dt, and then everything else can come down here. I will end up having to integrate both sides. I'll say t equals 0 is my throw time. Notice that I do have an initial velocity, which is negative v naught. Be a little careful there. And it'll just end at some arbitrary vy. This antiderivative we've done before, or you can just use a little u substitution, whatever you prefer. I'll go ahead and just write that. All right, multiply the gamma to the other side, exponentiate both sides. Don't forget that this log of a difference, the difference of logs will become the log of a quotient. Okay, now that's my velocity written in terms of the given parameters of the problem. It is sometimes convenient, though, to rewrite this in terms of things like a characteristic time and a terminal velocity. So you might remember from earlier that we defined the terminal velocity to be this g over gamma, or terminal speed, really. And we can see that's the case if I set my acceleration to 0 and solve for what is the speed when the acceleration is finally 0. M's all cancel out, and I will get a g over gamma for the speed. And then sometimes it's also convenient to define some sort of characteristic time, I'll call tau, which is 1 over gamma. And in that case, we can finish this off by writing this as the terminal velocity minus the initial launch speed, e to the minus t over tau, minus the terminal velocity, terminal speed. Okay, so that's my velocity as a function of time. Let's bring that to the top of the next board and we'll think about it. Okay, so here's our expression as a function of time for the velocity. Notice it's not the speed, this is the actual velocity. So at all times we're expecting this to be negative, but let's see what it ends up being. If v naught is greater than vt, then at time 0, well actually either way, whether it's greater or less, at time 0, this exponential is 1. The vt minus vt cancel, and I get my negative v naught. So we know there's going to be some sort of initial velocity in the negative v naught direction when time 0. Okay, we knew that anyway. As time goes on, though, if I take t to infinity, this exponential is going to die out. It's going to become 0 or approach 0 asymptotically. And I'll just be left with this last term, this minus vt. Now, if v naught, the speed, is larger than vt, the speed, then this negative number will be something else, something less negative. And in fact, we're kind of expecting there to be asymptotic behavior that approaches this terminal velocity. That's what it means to be terminal. So we're going to start here, and then the exponential is just going to make sure that we slowly grow and approach that terminal speed as a function of time. I haven't put anything on the time axis, but the characteristic time over which this happens, and by that I really mean the time at which this velocity has approached this terminal velocity to within 1 over e, 37% of itself, that's tau. So that's sort of the lifetime of this exponential. It's not really exponential decay, but it's kind of a mirror version of an exponential decay. So that's kind of what we're expecting our velocity to look like. So it'll start off with a great speed, and it'll actually slow down, still moving downwards, until it reaches, at least at infinity, that terminal velocity. Now, while we're at it, now that I have Vy, I can just integrate that one more time, and I can find y of t. I can also find the position of this particle as a function of time. So that will give me, well, I'll call it y minus my initial height. I guess I called it h over there. Should equal the integral, again, from t equals 0 up to some arbitrary time of Vy of t, dt. That's definitely just applying the fundamental theorem of calculus. And this integral is pretty easy to do, right? We're going to have, I'll just move this capital H to the other side. So it'll start at h. And then my integral here, well, the first term is going to have this constant factor out front. The antiderivative of e to the minus t over tau is going to be e to the minus t over tau. And then don't forget, we're going to multiply that by negative tau. I'll tack that on the end here. And then the antiderivative of our minus vt, and maybe I should put some brackets here because we're going to have to plug in our bounds and make sure it's all working. That's just a constant, so that'll be multiplied by t. But don't forget, we still do have to plug in 0. You should always worry about that when you've got exponentials, because you can pick up some extra ones and stuff by doing that. Okay, so if we do that, the 0 here will die off. The 0 here won't die off. I will be left with a 1 there, so I'm going to have to include that in all of my final calculation. So I should get h. I'm going to go ahead and take the minus vt term, bring it to the front, because it kind of looks like, you know, rate times time, the way you'd get in a normal kinematics problem. And then there's this extra bit, which is going to include the exponential. So that'll be, let's see, vt minus v naught. There's a tau here. And then the minus sign I'm kind of going to fold in here because I'll have e to the minus t and then minus e to the 0. So e to something minus 1. I'm going to use the minus to flip those. So this will be 1 minus e to the minus t over tau. And now we can kind of see what's going on if we, again, check our limits. So when t equals 0, that term is gone. This term is 1, and 1 minus 1 is 0, so I'm only left with that starting height. Good, we wanted to check that anyway. And then as t goes to infinity, we're expecting this term to just die out entirely. I'll be left with the 1. So there's a constant value here, which is just some number. This term, however, will make it go more and more and more negative. So it's not like you're going to asymptote to a particular height. You will continue to fall, but you won't continue to accelerate. Notice that this term is just linear in time. So in the far distant future, we are expecting that to not contribute. And maybe just as a quick little side graph here, we can put y and t just to get a rough idea of how this would look. So we start at some height h. Way down in time, we're expecting this thing to asymptote out to vt minus v naught tau, a constant. And notice again, if we choose v naught to be greater than vt, that'll be a negative constant, plus h, and then minus this sort of negative linear term. So the constant piece, so I'll just write this down, y approaches h plus vt minus v naught tau, that's the constant, this is a negative, minus vtt as t approaches infinity. That line on here will be h minus whatever. I'll just put this as vt minus v naught times tau. That's this distance from here to here. And then minus v naught or vtt. That's some line. So what we're expecting here is initially it'll drop pretty quickly. It will accelerate. We're expecting that. And then it'll sort of approach that. I'll use yellow here. It'll approach this line at long future times. Okay, and as a last little sort of check, we can check that even the derivatives make sense here. So for example, right here, we know that the initial slope should be v naught or negative v naught, which is a big negative number. And then way down the line here, we should approach this slope of negative vt, which is the slope of this dashed asymptotic line here. Okay, so I think that's a pretty good analysis of the velocity and position of a ball or whatever projectile it is thrown downwards at some initial speed v naught greater than the terminal velocity. QED.